Welcome everybody. We're here at Gear Expo and this is Ask the Expert Live. Today we're going to be talking about cylindrical gear cutting, and I've got 4 experts lined up here, and I'm going to give them each an opportunity to introduce themselves in just a moment. But I want to remind everybody in the audience that this is a participation event, so if you have questions to ask, please raise your hand. We'll get you a microphone. Thank you. So, experts, I'm going to start here with Tom Ware. Please introduce yourself and give us a little background about your experience.
Tom Ware, product manager of gear tools with Star SU. I've been involved in gear manufacturing since 1976, on both the actual cutting side as a tool research engineer and then also with Star Cutter and now Star SU.
Thank you, Tom. Oliver?
Hello, my name is Oliver Winkel. I work for Liebherr Gear Cutting Technology in Germany, and I'm working for Liebherr since 2004. I'm responsible for the application technology and also some technology development. And I studied mechanical engineering in Aachen University and made my PhD on gear hobbing there also.
Thank you, Oliver. Hermann?
Hermann Stadtfeld. I started rather early with the gear, in the gear business. I made an apprenticeship when I was 15 years old with ZF in Germany. But when you look at me, you can imagine it's not that long ago. However, later I also made a PhD at the Aachen University, and first worked a short time for Oerlikon, and after that for Gleason. I'm today Vice President Bevel Gear Technology and Research and Development at the Gleason Corporation in Rochester, New York.
Thank you.
My name is Hartmuth Mueller. I'm now 28 years in the gear business. I'm working for Klingelnberg and I'm in charge of technology and innovation.
Thank you all for being here. Let's get right into the questions. First up, how do I choose the proper cutting fluid for my process? Are there guidelines based on material, speeds and feeds, or process?
I can give an answer which you could call the wrong answer. My answer is, don't use no fluids, do dry cutting. We showed it in bevel gears that it works, and we converted the world of gearing in the bevel gear world. We converted that in the past 15 years from completely wet to maybe 5% wet today, and other than that, all dry cutting. But I know it's not the answer that the questioner wanted to hear.
Well, I guess, if you have to use coolants, the things to look at today, of course, is less and less people want to use the oil-based premium type coatings, coolants that they want to go to. They want to use the water-based. The big problem with that is making sure that your machines are capable of using the water-based coolants. Too often, you try and put water into a machine that doesn't have the proper seals, and of course the consequences are disaster.
Well, I'm actually not a real friend of water-based cooling principles, because what you see afterwards in the filtration system, this is something you don't like to see. There is everything biologically growing which becomes to a certain amount critical.
Yeah.
The only thing that's, from my point of view, relevant is with the cutting oil, you want to reduce your friction coefficient in between the cutting edge and the workpiece. The second thing is you need to have a clean cutting oil, otherwise you create scratches. And the third one, it needs to be temperature stabilized so that you don't have a thermal grow of your machine. All the other things are, from my point of view, not so really relevant.
Well, I would say from my side, it depends a little bit on the application. I agree, if you're in serial production and you're making hundreds or thousands of parts, I think you have the time to really optimize your processes and to make it suitable for dry cutting. But if you're a job shopper and you're making only 5 or 10 or 20 parts, you don't have the time to optimize each process. And so I think then wet cutting is very suitable. And also what you mentioned with the water-based coolant, I mean, if you have relatively small modules, it's possible to do that with oil. What kind of oil you like, I think you should discuss with the oil manufacturer. They have very good ideas. But if it comes to bigger modules where you use ICI tools and you bring a lot of heat into this process, then the oil is not capable to take this heat. So at that applications, at the big module machines, we typically use water-based coolant if necessary. For example, to temper the part to get the right quality. So it's really widespread in the application that we serve.
Thank you. Next question. What are the advantages and disadvantages of indexable insert hobs versus traditional solid hobs?
Okay, should I start?
Go ahead, Oliver.
I think that the ICI hobs especially have an advantage if you're cutting big modules. I would say over maybe module 8, DP4, that you have higher tool life and you can go for higher material removal rates. In the smaller modules, I see a contrary trend because typically the quality that should be achieved is not achievable with the tolerances you typically have in ICI tools. Also, the investment is a big point. A normal hob can maybe be purchased with $1,000, and these ICI tools, they are by far having a high investment.
No, I think that really is the big, it's a cost factor and also the quality factor as to what makes sense to use the ICI or the solids. There are also the advantages of the recoating turnaround time, which can also be seen as a disadvantage because the tool has to come off the machine where you can actually exchange inserts on the machine.
Okay, thank you very much. I want to remind the audience that this is a participation event. If you all have questions, just raise your hand. We'll invite you to ask questions of these experts. I'm going to go with another one from one of our readers, and this one is about skiving. So what is the difference between skive hobbing and the modern skiving process that everyone's always talking about nowadays?
They're quite different. Traditional skiving is, of course, the hard cutting process used with a negative rake hob tool to finish gear teeth. What we refer to is, in the single word of skiving, I guess we use the term power skiving to describe that particular process, or scudding as it applies to a certain manufacturer's equipment. But they're two totally different processes. The power skiving is a combination shaping type of material removing process, where hard skiving with the hob is a traditional hob removal method.
Herman, you want to add?
Yeah, I mean, there's a lot of confusion with the technical terms because we used to call skiving the hard cutting, and then people came up with scudding, and that was kind of company related. Then other terms like the power skiving came up. And in the meantime, we have hard power skiving. So we really have power skiving that is a hard finishing process, so that's also possible. And so among those processes, I think the word skiving was chosen because normally it is kind of a shear cutting of a chip differently than a regular cutting process. So basically, if you have a crossed axis gear, the sliding motion in length direction that you feel with crossed axis, that is used as a cutting motion. That actually has a side effect that a power skiving tool runs about 3-4 times faster than you would expect to run. So to have a cutting velocity of 1,000 feet, like you would have to have in tri-cutting with carbide, you need 3,000 feet circumferential speed if you have a 20-degree inclination angle. So really you have very high speeds with the skiving, and you take then, if it's a finishing process, only very small chips. But if it's a soft cutting process, you probably skim in 3 or 4 passes that material out with that relative velocity.
Hartmuth?
The big difference in between hobbing and power skiving is the tool looks completely different. For hard finish, for hard cutting, it's a typical hob, which needs to be rather precise to get a good surface finish. For power skiving, it's something like a shaping, it looks like a shaper tool. But the main difference from my point of view is that power skiving has a significantly higher flexibility What do I mean with flexibility? You can make internals, which is not possible by hobbing, and you can apply lengthwise crownings, which is also not possible with hobbing, except you accept the natural twist, which will happen by the hopping process.
Thank you, gentlemen. With the increasing adoption of high-speed skiving, what applications are still appropriate for gear shaping?
Maybe I take that question. Simply said, also skiving has interference. Right? So if you have a collision contour like a shoulder next to the gear, you have to investigate if you can skive it, because the necessary overrun for the skiving cutter is bigger than for the shaping tool. So fascinatingly, the shaping is called to be dead, but this is since 30, 40 years. Yeah? So all the time the design engineer is looking for the one or the other millimeter or which he can save in the design of the gearbox. He will do that, and then you still need shaping. But I think skiving is in all the applications that are in between a very nice opportunity that adds to the portfolio of the processes you can select. But there's still a lot of application which only can be shaped.
And there is another limitation for power skiving, and this is the module. If the module becomes too big, power skiving will not work because you overload the tool.
Very good, thank you. Next question, can I use power skiving to cut an internal spline? If so, what are the limitations?
Yeah, of course you can cut an internal spline because it's just another form of gear, even though it's non-involute. I have to admit that the software out there is not really readily available for non-involute shapes. So what people do is, if the spline has a flank angle of 15 degrees, they make a tool with 15 degrees. You implement corrections in order to get your 15-degree flank. So that's done today, but if, for example, if I was asked multiple times that some manufacturer has an entire portfolio of splines, then we would actually quickly write a software that complements for that, because you know the trial and error is in the experimental stage. As soon as it becomes industrial standard, you need something more professional. But to my knowledge, that's not really readily available today. It might be somewhere, but it's not readily available. But it's possible, and there are no limitations for splines. In the contrary, a spline has a really wide point width, and it is not that deep. So actually for power skiving, normally you could do it, depending on the quality, in one single pass and have very good tool life.
There are some other limitations. There are some diameter limitations in terms of because of the required rigidity in the tool. You can't have a 1/4-inch diameter tool and have it work properly. Also, because of the cross-axis angle, you do have some reach issues because of the cross-axis angle through the bore as well. So you do have other geometrical limitations to these parts.
Well, due to the crossing angle in between the tool axis and the workpiece axis, we also have a limitation of the face width. If the face width becomes too long, power skiving is not possible, and then we still have to live with shaping.
I think the question really fits well to the question before, because especially the small diameters with the high face widths, which are typically an internal spline design, it's not possible to get in. And so, yes, that is a shaping application.
Thank you, gentlemen. As long as we're on the topic of skiving, let's keep it going. In what applications does high-speed skiving compete well with hobbing for external gears?
Well, power skiving, we can achieve for a module something 2 to 3 millimeters. We can achieve the same process time with hobbing and power skiving. We get definitely a better quality in skiving, but the tool life is only 20% of hobbing. So it's a question, what is your target? Is your target just the cutting time, the net cutting time, or is the target your cost per part? But meanwhile, we get the same time in power skiving as we get it for hobbing.
The tool life might really be an issue, and Dr. Mueller is probably correct. However, what are we comparing? I would rather compare, like, that's where my experience comes from, using carbide blades. and maybe a stick blade cutter that is built so it's not a one-piece carbide cutter and it's not a one-piece coated high-speed steel cutter. And in that case, we can tri-cut. We can tri-cut with a decent tool life that might not be exactly as good, but the tool costs are lower, the tool refurbishing costs, like for everyone that has the equipment available. This is maybe typical for bevel people. If they also have bevel and cylindrical, have bevel sharpening equipment, then actually all the turnaround costs for tool resharpening, they are relatively low, the turnaround time is relatively fast, and it's tri-cutting, the most environmentally friendly. My opinion is tomorrow everyone should try machine.
And just in addition to this, if you use a stick blade system, you are very free with your profile because you can grind your profile on any blade grinding machine. So this gives you a high flexibility. Nevertheless, I had to take into account that the customers love this easy handling of a shaper tool. They say the stick blade tool is far too complicated. It's typical for a bevel gear guy to do something like this. Nevertheless, they like to have a simple tool, but they want to have both high tool life, good quality, and easy handling.
Well, I would take it this way around that I say, whenever you have a simple disc type gear, I would always hob it, because that's the fastest and most cost-effective process. Can even be done dry. But there are a lot of applications where two gears are on the same component, and so I can make both of them in one setup. Or even if I have an application where I can say, okay, one of the gears I can only skive and the other one I have to hob, then I need two machines. So if the capacity is there, it makes sense to skive the external gears. But in general, if I'm free of choice, I would always hob it.
I made the experience that companies that have bevel and cylindrical, maybe in the same shop floor areas, and people that are familiar with bevel cutting also, they actually don't hesitate to use the bevel system, use the stick blade system. They don't have this tradition and maybe this feeling that the most simple, straightforward cutter is this solid cutter. They see the advantages that they have for their bevel production, like I have to change the profile, the pressure angle, some profile curvature. I do it in the same afternoon of the same day. I can continue power skiving.
But I would like to object a little bit to this, was what Dr. Winkel mentioned. I think if you take into account the hard finishing operation, for example, you want to hone a gear afterwards. With honing, you have the possibility to compensate the natural twist of a hobbed gear, of a hobbed counter gear. And honing lives for then works excellent if you have a minimum stock. This means you need to have these flank modifications already in the soft stage. And there are significantly less limitations with power honing than with hobbing. There is one reason where I think hobbing and power honing, I think hobbing will have the majority of the market share for sure. But power honing, there are some interesting things if you also take into account hard finishing and if you take into account fast running gears. There we have to struggle with very different noise behavior characteristics.
Thank you, gentlemen. I'm going to switch topics on you now. The next question is, what new tool coatings are available on the market, and what advantages do they give me in terms of increased productivity?
Well, in the last couple of years, a change from the titanium-based coatings to the chromium-based coatings has significantly improved that. So we've got the aluminum chromium nitride-based coatings. The latest addition has been another coating that includes a top coat on top of the Corona base. And it's proven to be a very effective coating in very high temperature type applications. The basic aluminum chromium nitride coating seems to be a very broad-based coating and works across a lot of different applications, not necessarily needing that high temperature to be effective. But the new coating works very well in high-speed dry cutting, and we've seen some significant improvements.
Anybody else?
He said everything.
Okay, next up. What are the advantages of a cutter body stick blade system for high-speed skiving versus a traditional solid body tool? We covered some of that already.
I think we answered that almost, but maybe more specific. The cutter body with stick blades, if a blade breaks, for example, you throw away your solid cutter, but you can still change the stick blade and keep operating your stick blade cutter, and the cost were actually minimized. The flexibility, like a solid cutter, only basically the manufacturer of that cutter, which is not you as the user of the system, which is a tool manufacturer, will have to change that. Sometimes they are able to change existing cutters. Mostly they put them aside and make a new one because the changes were too radical. In a stick blade system, you put them through a blade grinder, and like I said, the afternoon of the same day. It's a little bit simplified because normally you like an all-around coating. Yep. But there is the possibility to also work with only front-face coating, and then really you go through the blade grinder, put it back in the cutter, and you're back in business. So the first investment for a stick blade cutter might appear, relatively high. But then as time goes on and you see how you can use this cutter for multiple systems, and the blades that go through have been proven to present the environmental most friendly solution. It's the least amount of carbide thrown away per gear produced.
I fully agree. I just want to add something more. If you have a shaper type tool, then you are limited in your relief angle and in your rake angles. If you use a stick blade system, then you can play with the relief angles and the rake angles because the regrinding necessity is not given for this shaper type tool. So you have in any case, you have with a stick blade system better cutting conditions.
That's actually an important point that I forgot. And on top of that, you don't have to correct for the grind off. The diameter changes in the solid tool. And in the stick blade cutter, you put it on the machine and run it over again. And you don't have to fear when the diameter changes. There are small geometry changes on the gear. They are neglectable, but they're there. In a stick blade system, they are not.
If you use a tapered tool, if you use a cylindrical tool, then the conditions for cutting are a bit worse, but you don't need to take into account the regrinding amount.
I absolutely understand that you're very enthusiastic are promoting the stick blade system.
Because we are bevel gear guys.
Yeah, maybe that's the reason why. And I like to comment, I think it depends very much from which application you're coming from. If you're in the bevel gear world and you have all the machines, you have the cutter setter, you have the stick blade grinding machine, you have the stick blade checker, you have everything there. I think it's a very nice option for all the guys who have that. But if I'm, let's say, new in that business and I try to decide which system I want to use, I would stay with the, let's say, conventional cutters because I just need one machine, which is a skiving machine, and not 3 machines to care for this system. So I think it depends what you really actually have in your facility or what you plan to do. If you have all that stuff, great.
I agree with that fully, but there is something that our colleagues here and us that we offer on the market in almost every country, and that is like blade refurbishing service. And we found that those manufacturers that are not really large enough to have all that equipment around, cutter building, blade grinding, etc., they send it to one of us for refurbishing, and this is a cost-effective possibility as well.
But we also should be aware that we need a special machine to set up the cutter precisely. This is another thing which is only available if somebody does bevel gears anyway.
Presentation of the Solution Center from WS Thermal Process Technology. We begin in 5 minutes.
Okay, next question. It seems like general purpose machine tools, 5-axis machine manufacturing. When should I consider cutting gears on one of those machines, and what should I watch out for?
The biggest issue with the 5-axis, I think, is rigidity, and actually then the capable cycle time of that machine. Most of the machines don't have the proper spindle horsepower to be very aggressive in their feed rates, so therefore their cycle times become much lower. And in the area of power skiving, because of the size of the spindle, rigidity becomes a very very significant issue in the quality that they're able to produce.
I think rigidity is one thing, but I would not overestimate it. From my point of view, something else is the issue. The issue is to have the tool on your shelf. If somebody wants to make a gear module 23 and he doesn't have a hob, he needs to wait, if he buys it from you, at least 2 weeks, maybe 3, I don't know. But the advantage is if you focus on the shortest possible lead time, then 5-axis milling makes sense. But you need to be aware of all the disadvantages. How long does the CAM process take? This means you have a 3D CAD model and then you make a CAM process, and this is where nobody of the 5-axis guys will teach you properly. They say, it's your CAM system. You can do with my machine whatever you want. My experience is that the CAM process itself even takes longer than a 5-axis milling operation. So the total time is different, and the guys who are sitting behind the CAM computer, they are quite expensive.
Now there were a couple of things said, for example, the power skiving. I believe that most of the machining centers don't really have the electronic gearbox connection between the work spindle and the cutter spindle, so power skiving is out in most cases. Then I also have the experience made in the past that when you use an end mill and you make a gear that size, or even bigger on a machining center, you can do it in ACMA 13. Seemed to be no problem. Takes a little while, but it seemed to be no problem. But as soon as you take in a more productive tool, like a disc cutter or even a hob, the problems occur. And then that accuracy that you were talking about occurs. Now coming back to the end mill or to the disc cutter, actually that was a topic that we have discussed in the past on several seminars, etc. The generating flats on the surface, the root fillet itself, the blend into the root fillet and the undercut and so on, appears to be always different. Not like the original involute wanted it to be. And that could be followed by interference, by pittings, by noise occurrence and so on. So it depends on what you want to do and what you expect from the gear to be manufactured and what the quantity is.
Well, I would add from my side, it depends very much on the application. So first I like to separate from 5-axis milling and doing gear cutting on a machining center. For example, if I have a very complex part where just, for example, a small spline is on, I think that makes sense to do this on a machining center because then the job is finished. The demands for that spline are not that high, and maybe cycle time, if you machine 6 hours on that part, it doesn't matter if the spline is cut in 5 minutes or in 10 minutes. This is what you also said, rigidity, quality, so on. But if you really consider gear cutting to be your profession, I think you should have a dedicated machine. That's the one point. The other point is 5-axis milling, I think also is a very nice opportunity to make spare parts or prototypes or something like that. But even there, the point is how big is the support? You mentioned the CAD/CAM system to tell the machine what is needed, and also that is often underestimated. Even on the normal machining centers, you know, all of us building high quality gear cutting machines. So everybody's used to the simple stuff like, okay, what is my approach, what is my overrun, where are my shifting positions, how is dressing working, for example, in grinding and all that stuff, and this is all covered. And if you look in the machining centers, it just can rotate the 2 axes, and that's it. And everything else is missing. So you need much more knowledge to handle these machines. This is very often forgotten from my point of view.
I fully agree to this. Nevertheless, there are some gears that can only be machined 5-axis, for example, herringbones. Well, we can't change this. But on the other side, I just want to add something. I talked about lead time. The big advantage of 5-axis machining is lead time. From my perspective, I would definitely go another way. I would not use 5-axis machining. I would use grinding into solid with profile grinding. There you have the grinding wheel on the shelf, and afterwards you have a very good surface finish. You don't need to run through the CAM process. That's what I would recommend to take into account, grinding into solid instead of 5-axis machining.
Thank you, gentlemen. The next question comes from one of our readers who's having a little bit of difficulty, so you're going to help him out here. And the question is, we're seeing excess feed marks in the tooth root of hobbed gears. What causes this, and what are the possible remedies?
Well, the feed scallops are a function of two factors, the diameter of the tool and the actual feed rate. So from a basic system, I guess you can look at going to a larger diameter tool that would make the scallop flatter, or you slow the feed rate down, which in most cases today is not practical from the perspective of cycle time. So a couple of the alternatives you can look at is to go from, if it happens to be a single thread application, if it's appropriate to go to a multiple thread application, now your feed rate per revolution slows and you get a smaller scallop depth.
I think the feed rates in the root, they're coming from the tip of the hob. And if everything is perfect, then you see in the root always more feed marks than you see on the flanks because of the 20-degree pressure angle. There's about a factor 0.7 in between. However, if the feed marks in the root still seem to be excessive or unusually high, then it's probably a hob runout. Either a tip runout of the hob or the entire hob with its holder has a runout, because on the flank you don't really recognize it that quick. You recognize it quicker in the root.
That's what I also would recommend. Have a look on the arbor if you have a wobbling motion of the hop or if you have a simple runout. That's in 60% of all issues, it's fixture and arbors.
Thank you. Next topic is asymmetric gears. And so the question is, what is the best method for cutting them?
Every method is like every other method. Manufacturer can make asymmetric hobs. They can make asymmetric disc cutters. On a machining center, you can, with any kind of tool, make an asymmetric gear. So I don't see really the question too justified that there is a problem of, it's probably only if you look in the catalog of a tool manufacturer, you're not going to find that asymmetric hob. And then you have a problem that your machine setup person puts it the wrong way on the machine. And you got the steep flank where the flat flank is supposed to be, and you got confusion there. Actually, what I saw, that was that asymmetric gears are more done with dog clutches for shifting and so on than really for the gears. There's always the claim that there was a German automotive manufacturer that did in small size manual transmission cars asymmetric gears. When we looked at it closer, it were just the shift clutches. The gears were not asymmetric. So it's very difficult actually to justify it in mass production. But I think it's possible with any of the processes. And any of the tool manufacturers, hob manufacturers, you can order an asymmetric hob. It's just not in the catalog, and there is not a good ACMA standard or DIN standard or ISO standard on it today.
Well, with asymmetric gears, you can play a little bit more in which we can balance a little bit more in between root bending stress and surface stress, contact stress. Because with the asymmetric gear, you have a lower crowning in tooth height direction, and this gives a little help to a better stress distribution, but you get a shorter line of contact.
Exactly.
So if you increase the tooth height, asymmetric gears will play their benefit at the cost of a loss in root bending stress capacity. But to the question, I think it depends on the volume. If you have a high volume, then you should look for an appropriate hob, and that's it. If you have low volume, again, grind into solid. That's the fastest way. Then you can make any profile angle out of the shelf.
I think I have an idea where the question comes from, because I agree that in general every cutting principle is able to do asymmetric gears, no matter if this is hobbing, generating grinding, profile grinding, whatsoever. And by the way, there are serial productions of asymmetric gears. The point is, all the mathematics that you know from your cylindrical gears is not valid anymore, starting from modifications, starting from MOB, whatever. So you need someone who supplies your machine which is able to take care of that. You need different mathematics to get these processes running. It starts with hobbing, it starts with the modifications, it goes to grinding, indexing, dressing, and so on. So if you find someone who is able to have this software on the machines, then it doesn't matter which process you select.
Thank you, gentlemen. I have another complex question, so bear with me here. This comes from a reader. We use a ground planetary gear set and experience a noise with a frequency of once per revolution of the planets. Spacing and runout are AGMA 13, and the surface finish quality is excellent. What can be the reasons for the noise? Which features on the gears should we look for?
I experienced things in the past that the soft geometry and the ground geometry didn't fit well. So if there was a run out in the soft geometry, and depending on how the work holding was for the hard machining, and the journal grinding, so was it done with a pitch line chuck and centering out or averaging out the teeth, or was it not? Was the part quenched in a press, or was it just free hardened? All that might have the implication that you have a run out. Oh yeah, and if in the hard finishing process, and for internal gears I have seen that often, that the root is not ground, that there is a blend. Now you look at the root around, you see all of a sudden you see a step on the one side on flank one, and then all of a sudden the step gets smooth, and now you see a step on the other flank. So the step wanders because of the wobble or the run out that was in the soft geometry. Now the planet actually will hit that 1/2 revolution, that step on the one side, the other half revolution maybe no indicate. So I remember those cases in the past, particularly with with internal planetary transmissions.
Surprising for me is that it's with every revolution of the planet. So we should know the number of teeth.
Yeah, if it was every revolution of the planet, then did you say that the
planets?
Once per revolution of the planets.
Yeah.
Then I would say it would indicate the case that I was talking about, only that maybe the work holding was okay, but for example, the stock division was off. If he has an interference step on every side, and if the planet in addition has a tip run out, then that's possible.
Yeah. Nevertheless, I would also take into account the planet carrier. So this is also something where you can usually have noise issues. And this is one thing we need to be aware of. A lot of people think the better my AGMA quality is, the less I have noise issues. That's not reality, gentlemen. Sometimes it's even worse. So the noise perception and noise issues are not directly related to gear quality.
Thank you. The hard finishing of planetary rings becomes a problem if the ring diameter is below 8 inches. Is there the possibility of a hard power skiving? And if the answer is yes, what tools are used and what surface finish can be expected?
Yes. Yes, the fact it is being demoed here at the expo. So yes, it can be. I can't give you an answer on the actual surface finish that they're able to produce right now. I haven't seen those measurements, but yes, you can hard power skive an internal ring. I mean, obviously, geometries are going to be a major factor on what is going to be or not going to be successful. And at this point, I don't think we have any good answers on tool life. Is it going to be a practical solution? And the old adage, we can do anything once, maybe one of those situations where on a production basis it may not be a practical solution yet. But certainly it is mechanically able to be done.
I'm wondering about the question. We just developed a job for an automotive manufacturer that was below 6 inches. That was a transmission ring for an automatic transmission, about that wide in face width, and it was hard power skived. And we used T-land technology and stick blades, and we achieved an AGMA quality of 13 during a run that was only 100 parts, but it was the number of parts that we had available. The cutter was documented afterwards and still looked pristine. The surface finish had an RA of 0.3, also the waviness was low, so every single criteria was beating grinding by far. So I think that is the process of the future for certain size rings. I agree when it gets under 4 inches, then things getting even more complicated. But I would think between 8 and 6, 5 inches, that's still very much possible with decent tool life.
I fully agree.
Thank you. For large gears with hundreds of teeth, how do you maintain spacing accuracy when teeth are finished machined via a form milling cutter? What specific types of machine tool technology and process controls will accomplish the task?
Just an anecdotal answer. Professor Opitz in Aachen, he had to make a gear that had like 3 meters diameter. And he put in a single indexing process. And when he was done, he missed half a tooth. And that anecdote was told to us. And I calculated that for getting a DIN quality of 4, he could have 10 or 12 teeth before, he could have just measured and averaged it out, and it would still achieve a DIN quality of 4. So, just cut your teeth and then the rest just split it up.
Well, I would say first, we talked about ICI tools. So you need to have a very high tool life because you don't want to change inside the gear, the cutters, the inserts. So that is a typical application for an ICI form milling cutter. Number 2 is that you have different strategies. How do you do the indexing? You can do this gash by gash. You can jump over some gashes. You can make some kind of a pendulum indexing, like from profile grinding. So there are software features which support you in that way. But I think a combination of both makes sense. And by the way, this is also a typical example for wet cutting, to try to make sure that you don't have any temperature changes over this hour-lasting process.
Yeah, you're right. But I think one question that is often underestimated is the stress release. If you cut the gap, you have a certain stress release because every material has residual stress. So if you do it tooth by tooth, you have a different stress release than if you do it first gap here, the second gap adjacent, and so forth. So beside the thermal effect, you also should take into account the stress release, and then it should be able to make a decent quality even with form milling.
I can add on that typically you rough the gear and then you lose all the screws, you let the stresses out, you recenter it, clamp it again, and then you make the finishing. This is the way I would recommend it if you especially only have a single piece, and this should be good.
I agree that's the way to do it, but I have to actually counter Dr. Müller's last statement. Don't we know from bevel gears that skip index is bad news? Always. For stress release, it's okay. But it causes a very strange indexing pattern that gives you a very strange noise pattern, which has a once and a multiple per revolution frequency. So, and with the temperature, I slightly disagree with him. If we have a part that has 30 teeth and we power cut it dry, then we have kind of a first to last problem. But if you have a gear like off-aircraft gears are with 120 teeth, until we get to the other side, that part normalizes so nicely, the temperature distributes because you have so much time go by.
But I would avoid
Depends
this.
how aggressive the cutting is.
I'm a little bit conservative. If you're in front of a 7-meter gear with a 1-meter face width, which had a value of about $500,000, and you have to decide dry or wet, I apologize, I decided for wet.
No, you're right. My example was from the bevel world, and we normally cut one, put it in frank metal, and then make the next one, and the third one is in a good one.
Fairly okay.
But those times are gone too, because today really the name of the game is make your first part right.
Yeah.
So I agree with you.
And maybe also as an add-on, if your job is to make that gear in a very high quality, I mean, that is what hobbing is made for. And there are even hobs in that size available. So we also have people which make 10, 12, 60-meter gears in single index milling, and that's exactly the limit. Yeah? The spacing accuracy of the machine at that diameters is difficult to get in that tolerance is if you have to position gash by gash.
All right, thank you. I'm going to go back to power skiving one more time. Is it possible to apply crowning, tip, and root relief and lead modifications with power skiving? And what about integrating chamfering and deburring into the process?
The simple answer is yes. Most of the machines are capable of doing single flank cutting, so therefore they are able to do even asymmetrical crowning or lead tapers as well. So that part of it is definitely possible. To integrate without an additional spindle, to be able to integrate the deburring chamfer, I think would be a difficult situation to try and do it with that same tool.
The software that we have for power skiving on bevel machines, they actually have input items. That's length crowning, lead modification, tip relief or stub tooth or tip extension, and also corrections actually. With the existing hub, although we could quickly grind our blades, but we have corrections where we three-dimensionally move the tool, and we know that from the bevel world similar, that we can make pressure angle corrections even independent from the left to the right flank, which is for many people that are experienced in that field, unbelievable that that is possible. However, the chamfering, to my knowledge, there's a new system developed, and that might not be officially on the market yet, that actually doesn't use a second spindle. It uses on the same spindle something behind the shaper cutter that does a chamfer.
This is also something I would like to mention. We can make asymmetric lead modifications in a duplex process, machining both flanks simultaneously. This is what we know from bevel gears, helical motion, modified roll, all these things that works. Nevertheless, chamfering works. We can do it with the same tool as long as the face width is not too large. If the face width becomes too big, then with our additional motions we somehow run into collisions. The only issue that is critical is if you want to cut the tip with power skiving. If you have a power skiving tool which has a helix angle, then the tip area becomes very, very complicated.
You mean topping off, so turning the entire internal diameter?
No, if you power skive an external gear, and then the tip, if you want to machine the tip diameter.
Yeah.
And this is not possible because if you have this helix angle on the cutting teeth, and then you have these steps, and then it doesn't work.
Very good, thank you. I'm going to ask one more time for questions from the audience. If anybody has any questions for our experts, please raise your hand.
Sir, you look desperate. Please ask it.
Okay, no questions. Thank you very much. I'd like to thank all of our experts for being here today. It's been a great educational session, and I appreciate it very much.
Thanks for having me.